Hey, AP Chem. Today we're going to be getting into some thermodynamic terms. Now, in our first lesson for Unit 6, which is what we're in now, I had you guys copy down some of the thermodynamic terms and draw a picture. And we're going to be going over those terms in more detail today in this lecture. And I think it's one of those things where if I would have given you the notes and had you write all the terms down with the lecture, it would have been a lot. So we just kind of broke it into a couple days so that you can take some time to kind of look through it once, digest it, and then go through it a second time. So we're going to start off with our terms by talking about the system and the surroundings. And I should back up for a second. All these terms are kind of interwoven and connected together. So you'll see them kind of used with each other. And that's because thermodynamics and thermochemistry is kind of this huge topic. And so you're going to see these units, or these words and terms described a lot, so just be kind of prepared for that. So anyways, our first two words are system and surroundings. Now, the system and the surroundings together make up the universe, okay? When we talk about our chemical processes, the system is our point of view that we are focusing on. So it could be whatever. Like, I'm just pulling stuff off my desk here. Our system could be this jar. My system could be my entire classroom. It could be an eraser. It could be whatever. So the system is just what you are focusing your attention on. Now, typically, when we are doing calculations in AP Chem, we are focusing our calculations on the chemical reaction that's causing some sort of change to happen in terms of the energy in a chemical reaction. And so when we are thinking about signs of energy and stuff like that, which we'll get into in a little bit, I always think about, it's really done by like, be the chemical reaction. So think about it like, if I am the chemical reaction, what's happening to my energy value? And if I am the area which is around the chemical reaction, which we call our surroundings, what is happening to me? And I always think about putting yourself in that perspective is really important. So if you are the system, you are that point of view, and then everything else around you are your surroundings. And that's going to change a little bit. And again, it's an issue of perspective. So if I talk about energy transfer or something like that, and I'm talking about what's happening when I touch my water bottle, it depends on if I consider myself the system or if I consider my water bottle the system, because it's going to look different depending on what the system and the surroundings are. So it's important that we define that and that we are careful with the way that we do define that, because it's going to change the sign, whether a change in energy is positive or negative. So we have to just be a little bit careful with that. And as we go through more practice, I will give you a hand with that. Now, you heard me use the term energy before, and we've used energy a lot in the class without getting too much in the weeds about it, but welcome to the weeds now. So what energy is it's the capacity to do work or produce heat. And we use a capital E to represent that. And when we talk about energy in AP Chem, we're going to be talking about the joule to represent that, or the kilojoule. Now, of course, we know that the kilojoule is 1 kilojoule equaling 1,000 joules, but you probably have heard of the term calorie before. And a calorie is just a different way to talk about energy. So when you consume food, you consume calories. And in the United States, our nutrition labels are in calories, but in other places in the world, they're actually in kilojoules, because when you eat food, it provides you energy to keep your body running. And the way that it works is that 1 little c calorie, and you're going to say to yourself, Adimeier, capital, who cares? But 1 little c calorie is equal to 4.18 joules. A food calorie is a capital C calorie, and that is actually technically a kilocalorie. So what happens is when you think about consuming food, if you eat 1 food calorie, you are consuming 4,180 joules worth of energy. And if you think about 1 calorie is not that much, right? So if you think about a joule is like over 4 times smaller than a little c calorie. So it takes over 4,000 joules to equate to 1 food calorie. So if you think about how much you're eating in terms of energy every day, it's a lot of joules worth of energy, because it takes a lot to kind of keep you all running. Okay. Now, on the exam, they're going to ask you questions in joules and kilojoules, but I want you to kind of keep that number in mind. Okay. Temperature and thermal equilibrium. We've talked about temperature when we talked about the gas laws, and so you should be kind of familiar with the two values that we're likely going to use. It's either going to be Celsius or Kelvin, and your temperature is a physical property that reflects how hot or cold something is. Excuse me. And that has to do with how fast the particles are hitting the thermometer, essentially. So if you measure something that's hot, it's going to have the particles hitting it more, and the kinetic energy of the stuff inside your thermometer, if it's a liquid or whatever, is going to be reflected in a higher temperature. And then if the particles that hit it are slower, it's going to be cold. Now, what happens is if I take two objects that are different temperatures and put them together. So I don't have anything around me, but even this, okay? Let's say I take my water bottle again and I put my hand on it. When I feel the water bottle, it feels cold to the touch initially. And that's because there is a difference in temperature between my hand and the water bottle. So what happens is always, if I put two objects together that have different temperatures, the kinetic energy or the energy is going to transfer from the hotter object to the colder object, always. So you'll have it energy leaving one thing and then going into the other. In the case of my hand and the bottle felt cold, and that's because my hand was warmer and the bottle is colder. When that happens, the energy, the joules, physically transfer from my hand to the bottle, and that cold sensation that I feel is literally the energy leaving from my hand. If I let my hand sit on this bottle long enough, even now just sitting here because I had my hand on it, I can feel that it's a little warmer to the touch than I initially had when I first touched it. And that's because the energy from my hand left. So my hand is a little bit colder, the bottle is a little bit warmer, and that energy transfer keeps happening until the two objects are the same temperature. So once those temperatures are equal, then they reach a condition called thermal equilibrium. So again, if I take a hot object and a cold object and put them together, what will end up happening is the energy from the hot object is transferred to the cold object, and then eventually they meet at that same position. That is assuming that they have kind of a finite amount of heat or energy that's in them. So if there's a constant source of heat, that's obviously a different situation, but we're talking about two things that have like a static amount, an unchanging amount of energy. They will reach what we call a thermal equilibrium. It's kind of like with gases, how gases always move from high pressure to low pressure. Same thing here. Energy moves from the hotter object to the colder object. When we think about movement of energy, think about, okay, so if my hand is the system, my hand is losing energy out into the bottle. If the bottle is the system is gaining, and then it's negative for me. So it's all about kind of the perspective there. Okay, now you're going to hear this term kind of thrown around a lot, and it's heat. Heat is actually represented by a lowercase q in thermodynamic problems. And you might say to yourself, Q has nothing to do with heat, but they call it the heat quotient because I honestly think they kind of started running out of letters. And so the heat quotient is represented by Q. Now, Q is going to be measured in joules, and it's literally the transfer of the energy from that object, one object to another. So like when I had my bottle and my hand touching, if I could calculate the joules that left my hand, that would be the heat that left my hand. So heat is literally the energy that's transferred due to the temperature difference. Like I said, it's measured in joules. You convert it to kilojoules depending on what your problem is asking you for. So you need to be very careful when you do these that you read what the units are, because they're going to ask you to do different things, and you've got to be a little bit careful about that. Okay. Now, there is an equation to calculate heat. This is printed on your AP Chem equation sheet, and it is Q equals M times C times delta T. We will be getting into this problem a lot, but I just want to kind of give you that heads up. Delta T, by the way, is change in temperature. And again, when we get to calorimetry, we're going to talk about this a lot. Or it's calculated using a value called enthalpy. We'll get into the enthalpy issue in just a little bit. But when we talk about heat, heat is an energy that's transferred. If we talk about heat in terms of just strictly joules, it is the actual quantity transferred. If we talk about it in kilojoules or joules per mole, we are talking about it relative to how much reacted. So we're going to make sure we clarify that as we go along. And like I said, the quantity of heat is going to change depending on how much stuff is reacted. Enthalpy should not change. All right. Another term for you is specific heat. Now, specific heat is represented by a lowercase c, but it's not the speed of light. Technically, it's c with a lowercase p, but we're going to use c anyways. So you've got to make sure you keep your little c values separate. So specific heat, what it is the amount of heat per gram of a substance required to raise the temperature of that substance by 1 degree Celsius. So what that means is, I have a little list over here. Liquid water requires you to add 4.18 joules worth of energy to make 1 gram of water go up 1 degree Celsius. Okay. And if I want to cool the water down, I have to take out 4.18 joules for every gram to make that drop 1 degree. Solid water in an ice form is half of that value. So it's 2 joules per gram degree Celsius. Water vapor is about the same as ice. Air has a specific heat of 1, and some of these values, even all the way down the bottom here, lead has a specific heat of 0.13. So what that means is if I take a gram of lead and a gram of water, I have to add 4.18 joules of energy from somewhere, Bunsen burner, flame, sun, whatever, to move that 1 gram of water up a degree. Lead, I only have to add 0.13 joules to get that same temperature. So when we talk about specific heat is going to tell us kind of how quickly things heat up relative to one another. And water has a really high specific heat compared to most other things. We will get into specific heat in much more detail. You're going to hear me say that again and again, but we're going to talk about each of these things on their own. But I want to throw these terms at you just kind of to begin with. Okay, now, enthalpy is abbreviated with or represented with a capital H. So enthalpy is equal to the energy flow of a system, which we talk about basically as heat as well. But when we talk about enthalpy, we're going to represent that in kilojoules per mole versus the actual just straight up kilojoules. So when we talk about an enthalpy change, it's generally tied to some value in a balanced equation. So it's like, oh, it is, 50 kilojoules per mole of NaOH that does this thing, or per 2 moles of whatever. And so when we talk about enthalpy values tend to stay the same when we're talking about in the ratio of heat that's coming out for every mole of substance reacting. Like I said, terms get a little weird here. So we will see that, and I'll make sure that I clarify as we go through our lessons deeper here. Okay, now endothermic and exothermic. There are 2 terms. These you need to know really, really well. So when we talk about exothermic reactions, processes, whatever, when you think about exothermic, you want to think about negative, okay? Exothermic reactions and processes are things where energy flows out of a system and is a product, a consequence of that change, and it's denoted by a negative value. So what I mean by that is if, let's say again, be the chemical reaction. If I am the chemical reaction and through a change or a process, I end up losing some energy out into my surroundings, that is going to be a negative change of energy for me, the reaction, okay? So when I think about losing heat to my outside area, that is going to be a negative change, okay? So I am losing heat. The heat, I always say, is exiting, or the energy is exiting in an exothermic process. And as a consequence of it exiting me, I get colder, but everywhere around me gets hotter. So if I'm observing an exothermic process in a container, I am going to observe it getting hotter around the reaction because the reaction is losing that energy out. So if you have a chemical reaction that gets started and you feel hot, like even a hand warmer, if you've seen those, you shake them up and they feel warm to the touch, that's because it's an exothermic process, and that's a negative Q value for heat or a negative H value for enthalpy. On the opposite side of things, you have endothermic processes. Now, endothermic processes are where if I am the chemical reaction, I am taking in energy, or like I like to say, heat is entering me. So endo is enter, exo is exit. So if I am pulling in heat from my surroundings, that means I have a net positive Q value or a net positive H value. The area around me, though, is going to get colder. So to the touch, if you feel a beaker that a endothermic process is happening in, it's going to feel cold because it's taking all of the energy from its surroundings and pulling it into the reaction. This is a question that they very commonly ask on the test. So you want to make sure that you can differentiate between endo and exo, and that's really, really important. And know what's going to happen in the surrounding conditions. Because we aren't going to be around to do a lab potentially in person, it's going to be extra important that you can differentiate that. Okay, so like I had said, in an endothermic process, like let's say melting ice, when that happens, energy is going into the ice cube. So the area around the ice cube is going to feel kind of colder and it's going to actually melt. When we talk about like a flame, energy is coming out, and so the area around it is getting warmer. Okay, we will go into much more detail with this when I actually get a chance to talk to you, but just be aware that these are kind of some terms that we're going to be dealing with. Okay, like I said, when we get through these, as we see each individual topic, I'll go into much more detail, but to start off with, these are the terms you're going to know. Okay, so if you have any questions, please let me know. Otherwise, we will move on to talking about how we even get these things, how we measure it, what causes these changes. And we're going to, like I said, I was waiting to get into the weeds, but now welcome to the weeds. We're getting into it. So if you have any questions, let me know. Otherwise, good luck.